Next one, this is one very important concept which we discuss here, and this concept is of buffer solutions. Highly important for any competitive exams. Buffer solutions. Buffer actually is an English word which means to resist. These are the solutions which resist change in pH on addition of a small amount of acid or base. I'll give you an example here. If we add simply 1 mole of HCl into 1 liter water, initially this becomes 1 molar HCl solution. This will be called as 1 molar HCl solution, and its pH, as you can understand, this one will be 10 minus log of H plus ion concentration here. So we take here minus log of 1. You can understand how much that pH has changed, while actually the pH should have been how much of pure water? It should have been 10 to power minus 7. Molar would have been the concentration of H plus ions. So if you take minus log of this, minus log of 10 to power minus 7, then we would have got the pH as 7. This was the pH of pure water. But once you added HCl here, you say how much drastic change has happened here in 1 liter water. Even if we add just small amount of HCl, we assume here 0.001 molar HCl we have got. Even then, you see this will be 10 to power minus 3, and this becomes pH has changed to 3 from 7. Got it? Case is, these are the buffer solutions. The buffer solutions resist change in pH. If a small amount of acid or base is added into the solution, the pH does not change as drastically as in case of pure water. We will show it. First, we understand what are buffer solutions, how are they prepared. See, basically, we have 3 different types of buffer solutions. One type of buffer solutions are called acidic buffer. Acidic buffer. Other type, you call the second type, are called basic buffer, while the third type is known as salt buffer. Sometimes it is also called as neutral buffer. So 3 types of buffer solutions: acidic buffer, basic buffer, salt buffer. First one, what is acidic buffer? If you mix in water a mixture of a weak acid and its salt with a strong base, and its salt with a strong base, then this solution of this mixture behaves as an acidic buffer. Example we will pick up here. We take weak acid as acetic acid. Its salt with a strong base will be, we treat it with sodium hydroxide. So we get sodium acetate, CH3COONA. This mixture is going to behave as an acidic buffer, right? How to find its pH if this type of buffer is given to you? That's what we discuss now. See, acetic acid establishes equilibrium because of being a weak acid to give acetate ion and H plus ion. Now, sodium acetate, because of being a salt, we can assume dissociates 100% or almost 100% will be the dissociation. So we get here acetate ion and sodium ion. Now, one thing to understand here, in presence of acetate ion, which is a common ion as in the equilibrium, this equilibrium will shift backward. As a result, the degree of dissociation of acetic acid is going to get suppressed further. We assume concentration of acetic acid taken is C. Its degree of dissociation in presence of sodium acetate is alpha. So it becomes C into 1 minus alpha. We get C alpha and C alpha. We assume the concentration of sodium acetate was C1. So we get the concentration of acetate ion as C1 as well as sodium ion as C1. Now we are going to write equilibrium constant for acetic acid and we assume it to be Ka. This will be equal to concentration of acetate ion CH3CO minus into H plus ion upon concentration of acetic acid CH3COOH. Right. Now we substitute the values and concentration of acetate ion will be C alpha into concentration of H plus ion. We write it like this only. This is concentration of H plus ion upon concentration of acetate ion, which is C into 1 minus alpha. Now again see same thing. In this case, concentration of acetate ion again will be total concentration present in the solution, which will be C alpha coming from acetic acid, which we already written. But one more concentration of acetate ion comes by dissociation of sodium acid, which is C1. So this will have to be added here. So the total concentration of acetate ion in this solution will become C alpha plus C1, like this. Right. Now check here, C1 is concentration of acetate ion coming from dissociation of sodium acetate, which is a strong salt, strong electrolyte. C alpha is the concentration of acetate ion coming by dissociation of acetic acid, which is a weak electrolyte which has got further suppressed in presence of strong electrolyte or common ion, acetate ion. So one approximation we take here, the C alpha will be negligible as compared to C1. This is the valid approximation. Second approximation which we take here is that alpha, which is degree of dissociation, which tells how much amount of acetic acid dissociates. We assume this also will be negligible as compared to 1. Why this one? Already I have been telling you, once we added acetate ion into this solution, this equilibrium equal to Lee-Chudley principle will shift in backward direction. Once it shifts in backward direction, its degree of dissociation suppressed. Now, if after taking these approximations we write the values here, it becomes C1 into concentration of H plus ions upon C. Now, we check the symbols which we have used. If you check, C1 is nothing but concentration of the salt which was originally taken. Similarly, C here is nothing but concentration of the acetic acid which was taken initially before the dissociation. We put these values as Ka equal to C1. Now we are putting as concentration of the salt. So it becomes concentration of the salt into concentration of H plus ions upon concentration of C, which is acetic acid. So concentration of acid taken initially. Right. Now we get H plus ion concentration as equal to Ka into concentration of acid by concentration of salt. We take minus log on both sides. We take minus log on both sides. So this minus log of H plus ion becomes pH. This becomes pKa, and we get plus log of concentration of salt by acid in this manner. This equation is one important equation, and this is known as Henderson equation. This is known as Henderson equation, which tells us how we can find pH of a buffer solution if concentration of salt and acid are given to you. Remember, the concentration of salt and acid to be taken here is the initial one which we have added here, not the final one after dissociation. This is how we get pH of a acidic buffer solution. Now, we come to second part, which is basic buffer. Basic buffer. Basic buffer, a solution of a mixture of weak base along with its salt with strong acid gives us basic buffer. Mixture of a solution of a mixture of weak base along with its salt with strong acid. Example, if we take weak base, we take ammonium hydroxide, and its salt with strong acid, HCl, will be ammonium chloride. This is NH4Cl. A solution of this mixture is going to behave as a basic buffer. If a basic buffer is given to you and they ask you to find the pH of this solution, how do we do it? See that. Quite similar to the first case. We have here ammonium hydroxide and ammonium chloride, NH4Cl. Ammonium hydroxide, because of being a weak base, it dissociates to establish an equilibrium between ammonium ion and hydroxyl ion. Ammonium chloride, because of being a salt, we assume it dissociates completely to give ammonium ion and chloride ion. We assume concentration of ammonium hydroxide is C and ammonium chloride, the salt taken, is C1. Now, again, this NH4Cl is producing ammonium ion, which is common with the equilibrium here. So, it is going to exert common ion effect, and due to this common ion effect, this equilibrium will shift in backward direction. As a result, the degree of dissociation of ammonium hydroxide is going to further suppressed. We assume in presence of ammonium chloride, the degree of dissociation of NH4OH is alpha. So, concentration of ammonium ions at equilibrium will be C alpha, as well as hydroxide ions will be C alpha. Now, this is dissociating 100%, or so we assume. So, concentration of ammonium ion coming by dissociation of ammonium chloride will be C1, as well as chloride ion will be C1. We write equilibrium constant for this, and this will be that Kb, the dissociation constant for the bases, is known as Kb. Kb will be equal to concentration of ammonium ion into hydroxyl ion upon concentration of ammonium hydroxide undissociated. This becomes equal to concentration of ammonium ion. Again, we have to total concentration, which will be C alpha coming by dissociation of NH4OH plus C1 coming by dissociation of NH4Cl. So, this becomes here C alpha plus C1 into concentration of hydroxyl ions. We substitute like this only, concentration of hydroxyl ions upon concentration of ammonium hydroxide, which will be C into 1 minus alpha, like this. Now, again, see, we are going to take some approximations, valid approximations again. One of the approximations here will be that alpha in this case will be negligible as compared to 1. The reason you can understand now very well. Why? Because in presence of ammonium ion, this equilibrium might have shifted in backward direction. Already ammonium hydroxide is a weak base. In presence of common ion, the dissociation would have got further suppressed, as a result alpha will be negligible. So we neglect alpha here as compared to 1. This is the first approximation which we take. Second thing, if alpha is negligible, then quite obvious C alpha 2 will be negligible as compared to C1 here, if we had sufficient amount of ammonium ion. So second approximation which we take here is C alpha is negligible as compared to C1. We take these approximations and write the remaining part. This comes out to be C1 into concentration of hydroxyl ions upon C. Again check, C1 here is nothing but concentration of the salt taken initially, and C is nothing but concentration of ammonium hydroxide taken initially. So we write these values here and we get that Kb equal to C1 concentration of salt into concentration of hydroxyl ions upon concentration of base. We take minus log on both sides. Kb comes out to be equal to concentration of salt into hydroxyl ion upon base. Now from here we get here hydroxyl ion concentration of the solution as equal to, from here you see it becomes equal to Kb into concentration of base by concentration of salt. We take minus log on both sides. So minus log of this OH minus concentration becomes POH. Minus log of Kb will become PKb. We put here plus, so that gets exchanged. So we get plus log of concentration of salt by concentration of base. Right. Now this equation is another important equation, also called as Henderson equation, and this equation will be used for buffer solutions. What type of buffers? Basic buffer solutions. Third type of buffers which we have here are called neutral buffers, or better to call them as salt buffer. How to go for them? See, we are going to discuss now salt buffer, and a solution, this is third category which we are discussing. First was acidic, second was basic, this is salt buffer here. A solution of a salt of weak acid and weak base. Solution of salt of weak acid, weak base behaves as a salt buffer. Example, you take weak acid, acetic acid, and now this is mixed with weak base, ammonium hydroxide. The product, resultant salt of them will be ammonium acetate, CH3COONH4. This will be the resultant salt. A solution of this will behave as a salt buffer. How does it behave and how we find its pH? We are going to discuss it now. See, ammonium acetate, CH3COONH4, we assume it undergoes 100% dissociation. So we get here acetate ion, CH3CO minus plus ammonium ion. Right? Now we assume concentration of the salt in the solution was C moles per liter. This is C. So this will be C and this also will be C. One thing you can understand here, that both the ions here will undergo hydrolysis. So instead of showing their hydrolysis separately, we can show simultaneous hydrolysis of both of them with water, and this becomes acetate ion, CH3CO minus plus ammonium ion, NH4 plus water, and they will give you by hydrolysis acetic acid, CH3COOH plus NH4OH. Concentrations of them as we have taken are C and C, and we assume the degree of dissociation in presence of each other is alpha. So what happens here? We get C into 1 minus alpha, C into 1 minus alpha, and this will be C alpha and C alpha. Now we get equilibrium constant for this, which will be called as KH, and KH will be equal to concentration of acetic acid into concentration of ammonium hydroxide upon concentration of acetate ion CH3CO minus into concentration of ammonium ion. Right. Now, for simplicity, what we do here is that both sides we multiply with H plus OH minus. So, the equation becomes H plus OH minus upon H plus OH minus. Now, see, if you see this part, this is nothing but Kw, right? Concentration of H plus into OH minus is nothing but Kw. Concentration of acetic acid, acetate ion, and H plus, if we take this part, this becomes 1 by Ka. And if you take this part, ammonium hydroxide, ammonium ion, and hydroxyl ion, this becomes 1 by Kb. If you write equilibrium separately, at that time, Kb will be equal to ammonium ion into hydroxyl ion upon ammonium hydroxide. So here it is reversed. So we are putting it as 1 by Kb. We substitute the values and we get from here that Kh equal to, this became Kw. So we get here Kw by Ka into Kb. Right. Simultaneously, we substitute these values, which are the concentration in terms of C and alpha. So it becomes equal to C alpha into C alpha upon C into 1 minus alpha and C into 1 minus alpha. Right. Now, as you can see that C gets cancelled. So we get here it as equal to alpha square upon 1 minus alpha whole square, and this will be equal to Kw upon Ka into Kb. Actually, in this case, there is no need to take approximation because anyhow this is going to be a simple calculation only. So we get from here that alpha upon 1 minus alpha equal to Kw by Ka into Kb under square root. Right? If we solve this, we can find alpha. Now, this is degree of dissociation of the salt in the solution. After calculating alpha, we can find that how much of the salt has undergone hydrolysis here. This is degree of hydrolysis. You can call that a degree of dissociation. You can call that. So this alpha or H, whatever you want, this can be called here. Right? Now, one small question we are going to discuss here, that suppose you have been given 500 ml of a 10 to power minus 2 molar acetic acid solution, and this solution is titrated with NaOH of same strength, and we are adding here 250 ml of 10 to power minus 2 molar NaOH solution. He asks you that find the resultant pH of the resultant solution. You have been given that assume Ka of acetic acid is equal to 10 to power minus 5. How to solve this problem? See, what we do here is that once you add acetic acid and sodium hydroxide, they react with each other because of being acid and base to give you sodium acetate and water. This gives you acetic acid, this gives you sodium acetate, CH3CONa plus H2O. Now, we calculate number of millimoles or moles. This is 500 ml, 10 to minus 2 molar. You multiply both of them, we get millimoles of acetic acid, which will be 500 into 10 to power minus 2, right? Molarity into volume gives you number of moles, and if you take volume in milliliters, you get millimoles. So we get millimoles of acetic acid as 5. Here you have taken 250 ml of 10 to minus 2 molar NaOH. Same way we multiply this also, and it becomes 250 into 10 to power minus 2, right? So here we get 2.5 millimoles of sodium hydroxide. Got it? 1 mole of sodium hydroxide as per this equation reacts with 1 mole of acetic acid. So 2.5 will react with 2.5, and 2.5 millimoles of acetic acid will be left in the solution unreacted. This is excessive reagent, this is limiting reagent here. Now 1 mole on reaction gives 1 mole of sodium acetate. So 2.5, you get 2.5 millimoles of sodium acetate. See, now if you see at the final composition of the solution, you have got acetic acid, which is a weak acid, along with sodium acetate, which is a salt of a weak acid with a strong base. As per the definition, the solution now becomes a buffer. And what type of buffer it will be? It will be an acidic buffer. We use Henderson equation here, which says that pH of a buffer will be equal to pKa plus log of concentration of salt by acid. We substitute the values. pK minus log of 10 to power minus 5 will be pKa for this, which will come out to be 5, plus log of concentration of salt. For salt concentration, this is 2.5 millimoles. If we talk about concentration, this will be 500 ml, which came from acetic acid, plus 250 ml, which came from sodium hydroxide. So total solution volume becomes 750 ml. So concentration will be 2.5 by 750. Similarly here, if you see, upon concentration of acid, 5 millimoles we have got, upon volume 750, this becomes concentration of salt and acid. One thing you can understand from here, one more thing, that in case of buffers, basically you need not to worry about the volumes. That's why we kept here volume. Automatically this will always get cancelled because both the acid and salt will be present in the same solution. So no need to bother about the volume because that always is going to be same and will get cancelled in the equation. So here it becomes equal to, this will be 2.5 not 5 because the left millimoles of acetic acid were 2.5. So this is 2.5, we get 5 plus log 1 which becomes 0. So pH of this solution comes out to be 5, right? Similar manner they can create the questions that we have got a this much molar acetic acid solution, calculate how many moles of sodium acetate should be added into this to make the buffer of this pH, this particular pH. Nothing will have to be done there. You will put the concentration of acid here. Here this will become X and put the resultant pH what he wants to ask you. You will get X from here, right? In this manner different types of problems can be solved